talk about a circuit that using nodal analysis to solve it, that may be a little more complex than maybe some very simple resistive circuits, just to kind of see how things might end up changing. Now remember, a lot of the reason you look at nodal analysis or mesh analysis is because you really care about sort of understanding how do computers make this work. It also gives you sort of a generic way to see how the linear systems get pulled together. So this is what we're going to be looking at. So imagine we have the circuit sitting over here, rather interesting looking circuit, where I have both a voltage source, a current source, and a voltage controlled current source. Okay. And a few resistors, because it just makes it kind of fun. But what's the first thing you do when you create a circuit? First thing you want to do is you actually want to figure out what are my nodal voltages, and I'm going to define an E1, E2, and E3. I could have defined another one here for VA, but that's already pretty well understood and defined, so we're just going to go with that. And then of course there's one other node, which is the bottom here, and we're going to label that one ground. In theory I could have labeled any of them ground, but that's kind of the most natural one, and there's usually physically a reason why you might pick one versus another. So then the question becomes, well, how do I begin to look at the matrix that I might create for the solution, which is going to be, in a nodal case, remember, going to be a set of conductances is a matrix times a vector of voltages equals current. So it's basically a form of Ohm's law, but knowing that I'm dealing with conductance, voltage, and the conductance and voltage give you a current. Okay, so how do I create these? Well, one of the things I notice is that the diagonal elements are going to always be what is the sum of all of the conductances of that node. So we see for E1 I get R1, R2, and R3. When I look at E2 I get R1 and R2, and these are conductances, so it has to be the inverse. And the third one I get R4 and R5, so again now I'm going to be dealing with conductances and things that are going to be sitting there as sort of as the inverse of the resistances that are labeled. Great. So now we begin to say, okay, I can see the diagonals. The off diagonals are typically going to be the resistances between those nodes, such as R2 or R4, and so we see those come out fairly easily. We have a current source going into E3, so there's your IA. We also kind of have a current going from VA through R1 into E1, and that kind of gives you a current term. And that gives you that's sort of where this additional term comes from. Now if you looked at it and you did it as a 4x4 matrix with VA in there, you would actually see the resistive term, and that'd be another way that you could get it. So there's a couple ways to look at it depending on your experience and the way you're going to be coding things and putting things together, or just even trying to do it by hand. The last question is, where did this GM come from? And that GM, of course, also corresponds to a 0, comes from this structure. Now you know that this is GM VB. VB is the voltage across R5. That VB is then also equal to E3. So another way to talk about it is that this is GM times E3. All right, that's cool. But that now becomes the current going into E2. Well, you could imagine that as being something I would put on this node. And you go, oh, well, that'd be GM times E3. But I'd really want all the E's on this side, not over here. So I need to move it. And how I move it is simply shift it to the other side. So I subtract GM E3 from both sides, which then pops GM here. Now you might go, wait a minute, where'd the E3 go? Remember, this is a matrix vector multiplication. E3 will get multiplied here. So this begins to give you your structure. Now, of course, once you have your matrix, you say, well, now let me take a look at particular values, and you can evaluate it. Now, I've done a normalization over this in terms of getting the variables, in terms of dealing with being mega ohm and microamps. These are consistent units. So when I do that, this is the matrix that I'm getting, right? So you could imagine, think this is a matrix times 1 over mega ohms. This is the matrix that is times 1 microamp. Same thing, this would be completely consistent. But now I get the structure where I know that effectively this is now in volts, and then I solve it. Well, you simply just put this into your favorite system to solve linear equations, whether this is MATLAB or some other form for solving, doing matrix inversion, and you get the solutions for E1 through E3 as these values. Now these are 2 are millivolts, this one is volts. So as a result, this gives you a way that you could actually do and calculate this. And again, remember, the reason for doing this is not because necessarily this is the best way to always solve circuits, but it gives you some really good intuition, as well as also what happens if you were actually to numerically compute these values.